Hello, students. I wanted to take a few minutes to talk about Newton's laws of motion as a whole here and just review some of those important relationships that Newton's laws talk about, just to make sure we're all on the same page before you complete your review and go on to the test. Now, first of all, let's look at the first two laws. I know there are three of them. We'll get to all of them, but the first two, because they both kind of talk about net force. Newton's first law is all about what happens if there is no net force on an object. And we know that's pretty much an object's going to keep doing whatever it is it's doing, being at rest, staying in motion, or whatever. And then second law addresses the other side of that coin. What if there is a net force on it? So let's look at this idea of net force, because that's really critical to understand how the world works. So what exactly is net force? Let's take a moment and talk about this. Let's look at this guy trying to push this big old box. It's obviously way too heavy for him. Now, based on his facial expressions and all, we can tell he is putting a force on the box. But the box isn't going anywhere. Why? Because friction is also putting a force back on the box. And if those two forces are equal, well, the net force on the box is zero because those two forces cancel out. They cancel out because one's in one direction, one's in the other, and they're the exact same amount. And this is where first law kind of takes over, or where we can see it. Because there's no net force in the box, it's going to remain at rest. It's not going to start moving. This idea can still be applied to things that move too. Remember, that's kind of the other half of Newton's Newton's first law. An object at rest will remain at rest, and the second half says an object in motion will remain in motion. And we see this with cars going down the road. If the engine in the car is putting a force out that's equal to the amount of force all the friction on the car is pushing against it with, those two forces balance out, and there's zero net force on the car. When this happens and there's zero on the car, it's going to stay in motion at a constant velocity. Does this ever happen in the real world? Sure, that's cruise control. That's what it's supposed to do anyway. Balance out friction. It's not that there's no force on the car, it's that the forces are balanced out so there's no net force on the car. So let's look at what if there is a net force. That's what second law is all about. Now, one of the main things about second law is direction. Net force and acceleration are always going to be in the same direction. So let's look at this little guy. He has obviously got his foot down hard on the gas pedal. He is doing his best to accelerate just as hard as he can. So what does that mean in terms of forces? Well, it means he's got his engine putting out a really big force that's way bigger than friction. So those two don't cancel out. Instead, we get a net force or resultant that is in the direction of the engine because the engine's bigger. And because there's a net force, there's an acceleration. And this guy will speed up. We can also use this kind of thinking to talk about cases where things slow down. Now, this guy is able to slow down because he's lifting his foot off the accelerator, making the force that the engine exerts on the car get small, and probably hitting the brakes, which is making the force friction puts on the car get really big. So this time, the net force, what's left after we subtract, is the other way. Okay? It's against the motion of the car. So again, net force and acceleration have to be in the same direction, but notice they're not always the same direction something's moving. In fact, that's how you get something to slow down, is your net force is against it, which means it's accelerating negatively or against the way it's moving, which is what makes it slow down. Now, we can talk more about this relationship between net force, mass, and acceleration that's described by Newton's second law. Basically, it says if a mass doesn't change, force and acceleration have to be directly proportional. So that's kind of fancy words. What does that mean? Well, if mass is constant, like if we're talking about the same object, the bigger force you put on something, the more it's going to accelerate. or the less force, the less it's going to accelerate. If we test this in lab, we would set up one cart, not change the mass, keep it constant, and start accelerating it by pulling on it with different forces. If we took that data and graphed it, we'd get a graph that looks like this. Acceleration and the accelerating force, the net force, are directly proportional. Nice straight line with a positive slope. And so if we look in terms of that equation that second law is famous for, you see here on my screen, m is the same size in both equations. It's highlighted blue because that's what we're keeping constant. And notice if we've got a big F, we've got a big A, and if we've got a little f, we've got a little a. Now, we can also talk about this relationship if force stays the same, but we put the same force on different masses. Okay. So when that happens, mass and acceleration are inversely proportional. One goes up, the other goes down. So if we use the same force, the more mass we're putting on it, the less we're able to accelerate it. It's just harder to accelerate bigger, more massive things. And if we were going to test this in the lab, we'd decide on a force to use on a cart, and we'd use the same force all the time, and we'd start piling more and more mass on the cart. And when we plotted the data, we'd get a graph that looks like this. Yeah, acceleration and mass are inversely proportional. As mass goes up, acceleration goes down. So that gives us that negative slope. And of course, if we look at it in terms of the equation, we see here I've got the F in blue over there, and they're the same size. But when we have a little mass, we have a big acceleration, and when we have a big mass, we have a little acceleration. Now, I promised you we'd talk about that third law of motion. We'll talk about that too. Instead of in terms of net force, whether there is or isn't, Newton's third law is all about force pairs. In fact, it's a law that forces always occur in pairs. In fact, I think Newton said that when one object exerts a force on a second object, the second exerts a force back on the first of equal magnitude in the opposite direction. But that boils down to this cool little way of saying it that I've got on the screen now. A pushes B equals B pushes A. When you're trying to identify examples of third law, if you can say it this way, it's an example of third law. But if you can't say it this way, it's not third law. So look at our example here. This person is pushing against another person. As they push on each other, however hard person A pushes on B, person B pushes back the same. In fact, it's not possible for one to push on the other harder than the other pushes back. And most people go, wait, that's not right. What if one guy's strong? It doesn't matter. One guy, in fact, can just hold still. But remember, if I clap my hands, there's only one force. There's only one slap, and it works on both my hands. Same thing here. It doesn't matter who's trying to do the push. The actual contact force is the same both ways. Person doing push-ups is a great demonstration of Newton's third law, because A pushes B equals B pushes A can be seen in terms of the push-up as the person pushes the ground and the ground pushes back on the person. And of course, car crashes. We don't like to think of them, but they're great examples of third law also. You see in this picture that I have up here, a car and a truck have collided, way different masses. And in terms of third law, what that means is, since A pushes on B equals B pushes on A, the car pushes on the truck with the same force the truck pushes on the car. The truck doesn't hit the car any harder than the car hits back. And everybody goes, but wait, are you kidding? The car is smashed, the truck's barely damaged. But that's not about third law. Now you're thinking about second law, maybe even a little first. Third's just talking about the impact. And it's one impact, so it's the same both directions. But the results of that impact really depend on second law. And second law says the force is the same. That was third law. So you see on the left side of the equation, a little m, that green car, gets a big A. He gets a big change to his motion. But the big M, which was a truck, gets a little a. He gets a small change to his motion. And then, of course, we can further think about that in terms of first law. Why does this happen? What's this whole mass acceleration? Well, it really boils down to the fact that the mass of the car is way less than the mass of the truck, as we saw in the last equation. And that means the inertia of the car is way less than the inertia of the truck. And remember, the inertia is that tendency to keep doing what you're going to do. Since the truck has way more mass, way more inertia, it's going to keep doing what it's doing and the car has to give. That's just the way it works. So I hope this has helped you out, got you to think about those 3 laws of motion just a little more. See you later.